Hey guys, Ms. Hydrick here with your Space Objective 1 video. The objective is to describe components of the universe, including stars, nebula, and galaxies, and use models such as the Hertzsprung-Russell diagram for classification. You can see that you have 9 essential questions that you need to answer during the course of this video, as well as an action item. So if you have not set your Wix up yet, now would be a good time to pause the video, get your Wix set up, and then you can continue. Now that your Wix is set up, let's begin. The universe is everything that exists, including all matter and energy. If we were to zoom in, starting with the universe and working our way in, we have galaxies, and in front of you, all of the speckles of light that you see, those are galaxies or groups of galaxies. And within the universe, there are 100 billion different galaxies. Within each of those galaxies, you will find structures such as nebulas, solar systems, and stars. And there are hundreds of billions of stars found within each of those galaxies. Now, the universe is big. It's really big. So to get an idea of just how big the universe is, we are going to magnify the universe so we can get an idea of the scale. So we're going to zoom out. We'll zoom out slowly so you don't get sick. All right, there we go. So we start with the observable universe, and we are going to simply zoom in to a single area within the universe. So we zoom into the local universe. And within the local universe, there's an area known as the local group, which is all of the different galaxies that are nearest to our galaxy. And we are in the Milky Way galaxy found within the local group. The Andromeda Galaxy, which is the next nearest spiral galaxy to our own. So now we're going to enter into the Milky Way. Now notice as we zoom in, most of the area that we see is black. That's space, and within space there's nothing. And so we find these galaxies, hundreds of billions of galaxies, spread all over the universe. But again, most of the universe is just empty space. Now within those galaxies, we find these structures called nebulas, and these are all nebulas found within the Milky Way galaxy. Nebulas are areas of dust and gas where planets and stars form. So we'll begin to see different stars. Notice these stars have different colors. Some are red, some are yellow, some are blue. And we eventually zoom in enough where we see the sun, which is the one star found in the center of our solar system. And our solar system is composed of planets and asteroids and meteors and comets and moons, and there is the Earth. And so that's where we're going to end our journey. So the universe, you can see from that trip, is really big. And so measuring these enormous distances in space requires an enormous unit. And the unit that we use to measure distances in space is the light year. And so we will be studying the light year a lot more within this unit as we work on our light years lab. But now would be a good time to pause the video and complete your action item. If you don't want to do your action item right now, just make sure that at the end of the video you remember to go back and do that. Most of the universe, like we saw, was empty space where no matter is present. We call this empty space a vacuum because there's absolutely no matter. There are no atoms. There's no nothing. It's just nothingness. And within that nothingness, we find all of the galaxies, and within those, we find the nebulas and the stars and the planets. So if a rocket ship fires its engine in space, does anyone hear the noise? Well, the answer is no, because sound can't travel in the vacuum of space. Sound is vibrations that travel through matter. Sound needs a medium like a solid or a liquid or a gas for it to travel through. And in the absence of matter, like in space, sound cannot travel. What about light? Can light travel through the vacuum of space? Yes, it can. Light does not need a medium in which to travel, so light does have the ability to travel through the vacuum of space. That's how light from the sun, sunlight, reaches the earth. So within the universe, we have galaxies, and they're defined as giant structures that contain dust, gas, and hundreds of billions of stars. And we can find 100 billion galaxies within our universe. And galaxies can be classified by their shape. We have 3 categories of galaxies. The first one is called an irregular galaxy. An irregular galaxy does not have a definite shape. It can be all kinds of different shapes. Irregular galaxies are very rich in dust and gas, which are the necessary materials for stars to form. So where there's a lot of dust and gas, you're going to find a lot of new stars being formed. So irregular galaxies are made up of mostly new stars. Then we have spiral galaxies, and spiral galaxies are shaped like a spiral. They kind of look like a pinwheel or a hurricane, but spiral galaxies do have a lot of dust and gas as well. So a lot of new stars are also being formed within spiral galaxies. Now, spiral galaxies also have a lot of old stars, and we know that with this structure here in the middle. This is called the central bulge, and it is the area where all of the oldest stars are found. So galaxies really are formed from the inside out. You'll find your older stars in the middle, and as you move to the outside of the galaxies, the stars become younger and younger and younger and younger. The third galaxy type is the elliptical galaxy. They are shaped like round or oval galaxy structures. Now, within elliptical galaxies, there's very little dust and gas present. So no new stars are being formed because there's not enough dust and gas to form those stars. So elliptical galaxies are mostly old stars. In fact, the elliptical galaxy is nothing more than a leftover central bulge. And so eventually this spiral galaxy will be nothing but this leftover central bulge, and at that time it will be an elliptical galaxy. So galaxies kind of evolve from irregular galaxies into more organized spiral galaxies and eventually into elliptical galaxies. 90% of our universe is composed of spiral galaxies, which tells us that our universe is still relatively young. It's about 14.5 billion years old and probably has another 14.5 billion years to go. Nebulas are found within galaxies, and they're large areas of dust and gas spread out over an immense area. And this is where stars and planets are formed. And so here's a picture of the Crab Nebula, and all of these nebulas are found within the Milky Way galaxy, Orion, Cat's Eye, the Eagle Nebula, and these structures are called the Pillars of Creation. And so solar systems are collections of celestial objects that orbit a star. Now, celestial just means space, and so a solar system is a collection of objects found in space. And these objects orbit or move around a star. And solar systems can include things like planets, comets, moons, meteors, and asteroids. Stars are large celestial objects that are composed of gas, and they emit or give off light. They're the only structures in the universe that give off light. And so stars are composed mostly of two gases, hydrogen and helium. And stars do shine bright. And there's two different ways that we can describe a star's brightness. The first way is called apparent magnitude, which is how bright a star appears to be based on its distance from Earth. Our sun, for example, appears to be extremely bright, but that's only because it's very close to us. If I were to take the sun and several other stars and bring them all the same distance away from the Earth, then the sun may not seem very bright after all. At that time, then we would be comparing the star's absolute magnitude, or how bright the star actually is. And the star's absolute magnitude is going to be based on its size and temperature. The larger a star is, the brighter it's going to shine. The hotter a star's temperature, the brighter it's going to shine. And we can determine a star's temperature by its color. So the color indicates the temperature of the star. Now, Hertzsprung-Russell is a diagram that compares a star's temperature to its absolute magnitude, or luminosity. And this is really just a graph with an x and y axis, and the x-axis measures the temperature of the star, and that temperature could be measured in units such as Kelvin here, or even in degrees Fahrenheit or degrees Celsius. Now here on the x-axis, notice that on the right-hand side we have our lower temperatures, and our temperature increases as we move to the left, which is the opposite of how a lot of graphs are, their x-axis are measured. So be really careful when you are reading an HR diagram. Again, we start on the left-hand side with our hottest stars, so all of our hotter stars are over here, and you can see that they are in the blue color spectrum. So a blue star is going to be a hot star. And as you move to the right, the temperature is decreasing, with our cooler stars being in the red color spectrum. Now, the y-axis of an HR diagram measures the luminosity, or the brightness, the magnitude of the star. And right here in the middle, you can see that the luminosity is 1. That is the brightness of our sun. So the HR diagram compares the brightness of stars to the brightness of our sun. Any star brighter than our sun will be found at the top of the diagram, and any star dimmer than our sun will be found at the bottom of the diagram. So our sun, being a yellow star, would probably be positioned right around here on the HR diagram. You can see on this diagram that there are 3 groupings of stars. The first grouping is called the main sequence, and stars within the main sequence follow a specific pattern. Cooler stars are down here on the bottom where they're dim, and as the temperature of the star increases, the brightness of that star also increases. So that's the pattern of temperature to brightness within the main sequence. The second grouping of stars can be found up here at the top right-hand side of the diagram. These are our giants. Now notice if these stars follow the same pattern as in the main sequence. I hope you said no, because supergiants are cooler stars found on the right side of the diagram, but they're at the top, which means they're very bright. So they're cool but bright. So what characteristic do you think these stars have that allow them to be cool in temperature yet very bright in their magnitude? Well, they are giants after all, so it's their size. The size of these stars allow them to be super, super bright, even though their temperature is pretty cool. And the third grouping of stars are the white dwarfs, or the dwarfs. They can be found down here in the lower left-hand side of the diagram. Did they follow the same pattern as within the main sequence? No, they don't. And that's, again, because of their size. The white dwarfs are very hot in temperature, so you would think they would be very bright in their luminosity, yet they're found at the bottom of the diagram, which means they're very dim. And that's because white dwarfs are so small. So don't forget, when we're considering the luminosity or the brightness of a star, we have to take into account both the temperature and the size. Well guys, that's all for me today. I will see you next time.